So we are continuing from the last point that we have left, which was actually last time. We have covered Gaussian distributions, actually Gaussian processes. Now today we will be starting with an example. So x of t is a Gaussian process with zero mean and autocorrelation function Rx function given in this form. Okay. Now, the question is, part number one, is x of t, this random process, White and stationary? Okay. Number two, determine a sampling rate t such that the samples of this process, x of n, x and t, are independent and write the joint density for sampled process, first sample, second sample, and third sample. Okay. So let's look at the problem. Now, number one, the key point is this is a Gaussian process. This says a lot to us. And then zero mean is given. Autocorrelation function is, as you see, over here. Let me write it like this. Now, from this information, what do I know about Gaussian processes? I can write the PDF of the samples of this process in terms of Gaussian distributions. Okay? That is a defining property of Gaussian processes. So samples of this process, maybe x of n, is Gaussian distributed. But the question, part number one, now it's about the random process x of t. Is x of t White and stationary? Well, let me do this. Expected value of x of t is given as 0, zero mean, and Rx, let's say t1 comma t2 is equal to, let me write this like sinc function t1 minus t2. Okay. Of course, the sinc function is, let me write it over here, sinc of x sine pi x divided by pi x. Sinc function is a frequently used function. So we are defining this as its definition. Okay. And then we have that. Okay. Sinc t1 comma t2 is this function. So this is from the problem statement. Now, what's our conclusion? So this is constant. And this is a function of what we will call this time difference t1 minus t2. Sometimes we call this lag. It's a function of this lag variable. This thing is function of t1 minus t2, but not t1 and t2. Okay. So what's our conclusion? So this is hence x of t is White and stationary because it satisfies this constant condition, mean being constant, autocorrelation being function of only lag variable, time difference between those two samples. We are done with this. Now the second question. Find the sampling rate t. So I'm taking the samples of this process such that these samples, all of them, are independent. So how can I handle this? But before that, okay, let's find, how about this? Just one sample, xn, X and T distribution. So just, it's the marginal distribution, you may say, of a joint distribution. So this is just the nth random variable, okay, by itself. So it's alone. So what's the distribution? So we know that X of n is this sample, Gaussian distributed. Since this process, X of t, whole process, is a Gaussian process, so this is the reason that this tells us a lot about these samples. If it's a Gaussian process, marginal distribution, first order, second order, third order, all of those distributions are Gaussian distribution. So what do I have? That X of ns, you may say, normal distributed, let me say with mean and, let's say, variance. Okay? So this is our normal distribution, Gaussian distribution. Now the question is, what is the mean? Well, expected value of X of n is equal to, since this is equal to expected value of nt, mean function evaluated is equal to 0. How about this? Variance of this. So this is equal to variance. So can I write this as covariance of, well, how did I write this? X of n, X of n. Covariance. Okay? So I have autocorrelation function. So this is equal to Rx, well, let me call this expected value of X of n squared minus, this one, minus 0. Or let me write expected value of X of n parentheses square. Okay? So how about this one? This is, since this is expected value of nt parentheses square, now you see that this is also equal to Rx function evaluated at nt, comma nt. Okay, that is it, by just the definition, because I'm telling you for any t1, t2 value, expected value is, which is this, is function like that. But how about when these two arguments are the same? Well, this is not the exact definition, you may say, because if the arguments is 0, because t1 minus t2 is equal to 0, like in this case, if both arguments are the same, then I have, in the sinc argument, I have the following, sinc of 0, and this is equal to 1 actually. So maybe I should write this a little bit more carefully, when this is not equal, not this, but when x is not equal to 0, and I should write this as, when x is equal to 0, it's something like this, 1. Okay. So I will draw the sinc function instantaneously, but at the end of this calculation, by just evaluating this function, or this function, at 0, I get 1. So what do I have? X of ns and 0, 1. Okay. Gaussian distributed with 0 mean and variance of 1. Now this is valid for all n, because if I change the value of n, no, nothing to do. Okay. And this is a little bit expected, because if this is white sand stationary, that means that it's strict sand stationary for Gaussian processes. I shouldn't be, sensing a change if I sample it at a different time. Okay, that is the issue. But this wasn't the question. Well, the question is, I want, so this is 0 mean unit variance. There's another sample 0 mean unit variance. So how can they be independent? Okay, that is the question. So we know that x of n is n01, x of m, another sample, n01. But we need to assure that x of n, this is like written like this. Okay, x of n and x of n are independent. Okay, so how can I do that? Do you remember? For Gaussian distributions, there was something special. So this is recalling your probability course, but I will show why this is true. Remember, for Gaussian distributions, if, let's say, x and y for jointly Gaussian distributed random variables, okay, for jointly Gaussian distributed random variables, if x and y are uncorrelated, do you remember this? You don't remember it? Then we say that for jointly Gaussian distributed random variables, if x and y are uncorrelated, meaning that covariance of x, covariance of y is equal to 0, this is the definition, then x and y are independent. Okay. The reverse implication is not correct. So what do I mean? Well, sorry. The reverse implication is if x and y are independent, they're always uncorrelated. Okay. We have always a case like that. If x and y are independent, this is always true. But only for Gaussian distribution. Now you have Gaussianity and uncorrelatedness, then independence also guaranteed. Now how can I, build upon on that? So I need samples which are uncorrelated. So let me then sketch this Rx function, Rx of tau. This is our sinc function. So this is sinc of tau. Okay. So as we have said, this takes the value of 1. Okay. Over here. And if you evaluate this sinc function for small x values, as x goes to 0 by L'Hopital's rule, etc., you get 1 also. Or you can approximate the sinc function with small argument as the argument itself. So argument itself divided by this, you get 1. Okay. So no surprises, this function approaches 1. So the value at 0 is also defined as 1. How about the first 0, second 0, third 0 on the right? If you check this. So how can be this sinc function equal to 0? If the numerator is 0. So numerator is 0. This is a sine function. Either this argument is 180 degrees, okay, or 0, okay, 360 degrees. So it's equal to 0 when tau is equal to 1, or x over there, 1, 2, 3, for every integer. Do you agree? So this goes like this. Okay, we have a function like that. So this is the autocorrelation function. But it says over here, covariance function should be equal to 0. The covariance value should be equal to 0. But remember, this is also equal to Cx of tau, since expected value of this is equal to 0. Okay? They are equal to each other. So if I have two samples uncorrelated, that means that if x of, let's say, t1 and x of t2 are uncorrelated, that means t1 minus t2, time difference between them, which is tau, should be such that, let's say, time tau x, sinc tau x is equal to 0. Okay. Do you agree? Well, something extremely simple. Covariance of xt1, xt2 is equal to sinc t1 minus t2 by this. So how can this be equal to 0 if and only if this time difference, okay, should be one of the zeros of this sinc function. Okay. So T1 minus T2 should be one of the zeros of sinc function. Sinc function, okay. So this is only for 2 samples. So if you have 3 samples, 4 samples, 5 samples, and so on, so what's your conclusion? How can I select my sampling rate? So please remember, now x of t is entering. I have this kind of a converter, and I have x of n going out. This is this sampler. Okay, I'm sampling. So can you give me a t value for which the separation between any samples is an integer? Okay, it should be, if the separation between any 2 samples is an integer, then you will say that those 2 samples are uncorrelated. Am I right? If the time separation between. So let's see, t is equal to 1 seconds gives us x of n is equal to x of, let's say, nt. T is equal to 1, which is totally, which is composed of independent samples. Okay. Is this clear? A little bit. Okay. Now, if this is not clear, let's give one more chance then. Now, what was the last part of the problem? Joint distribution of, let's say, x1, x2, x3. Okay, so this was the problem. I think everyone is with me for this part. If I have a univariate, if I have a single random variable, this is the result. Now, if I have multiple random variables, of course, it's a little bit more complicated, but this is the case. For jointly Gaussian distributed random variables, I have this. So how can I write this density? F of, now x1, x2, x3, and clearly I want to write it like this for shorthand form. Okay. This is my x1, x2, x3, 3 random variables. So this is the joint Gaussian distribution. I will try to apply this. 1 over square root of 2 pi to the power 3. So this is Cx matrix. Determinant square root. Okay, I have this. Now e to the minus 1/2 x minus mu x transpose. This looks like a complicated function, but actually it is one of the simplest functions that you can come up with, because this is what we call quadratic product. There are squares over here. But let's try to evaluate it right now. Now, what is this vector? Mean vector. So it's the mean value of these 3 quantities. That is 0, 0, 0. Because as we have written, every one of these samples are 0 mean. Okay, that is good. Now, how about the Cx matrix? Cx matrix is something like this. So if I write, for example, x1, x2, x3 over here, x1, x2, x3 over here. So this becomes covariance of x1 and x1. Covariance of x1, x2. Covariance of x1, x3. Do you see this? Row, column. This is the definition of Cx matrix. Covariance matrix for the 3 by 3 case. Okay. Now, do we know this quantity. So if I can find this matrix, we are done. That is the end of density writing. So because there is nothing else left, this X vector contains these samples and so on. So what is this quantity? Covariance of X1 and X1. It is 1 because it's the variance of X1. Okay. So I have 1. I have 1. I have 1 over here. How about this X1 and X2? Now, what is the separation between those two samples? According to our, t is equal to 1, 1 second. Okay, 1 second. So you evaluate this covariance function at 1, you get 0. So this is 0, this is 0, this is 0. All of them are equal to 0 because this is 1 second, this is 2 seconds, so on. So at the end, I get identity matrix over here. Okay, for this. So what's my final result? According to this, my final result is 1 over 2 pi to the power 3. So determinant of identity matrix is 1. Square root is 1 of 1 is 1. I don't write this. Times e to the minus 1/2. So let me write this vector. Or let me write it like this. X transpose. Cx is identity. X. Am I right? Its inverse is also identity. So how about this one? 1 over 2 pi e to the minus 1/2 x1 squared x2 squared x3 squared. Do you agree? Well, the reason is this x vector, by definition, these are the variables x1, x2, x3. These are the parameters of this function or density. Okay, that is the end. So what do you see? For the independence of 3 random variables, this is supposed to be written like this. Do you think I can write this joint density as a product of 3 densities, and every term of this density is Gaussian distribution with 0 mean and unit variance? Okay. So clearly, for example, this one is this part. This one is, because if you are multiplying, you are adding the exponents, right? You clearly see that. So this is this conclusion actually. For Gaussian distributed random variables, if the off-diagonal terms are equal to 0, all of them are equal to 0, off-diagonal terms of this matrix are equal to 0, then you see that I always have such a result, and this gives me that now this joint density is simply the factorization of marginal densities. So this is the condition required for independence. So we also verify this. Actually, we are very happy. Now, what we have verified? We have verified this calculation. We have remembered this. So after remembering this, we have selected this t value. So once we select this t value, we have also seen that why this conclusion, why this, the note that we have remembered for the finding of t value is valid. We have also seen this. So the main issue is, if this covariance matrix is a diagonal matrix, as you see, then its inverse will be also a diagonal matrix. Then if you multiply them, there won't be a cross terms like x1 times x2. Okay? You'll be having terms over here after this multiplication, just like that. x1 squared, x2 squared, x3 squared. And you can write this, you can collect this x1 squared in a function, x2 squared term in a function, and these are the Gaussian distributions, as we have said before. Okay, so this is the example on Gaussian processes. Now, let me continue with the following. Now, I would like to discuss this important topic actually. So this is LTI processing of linear time invariant processing of voice and stationary random processes. Okay, so my final, let's say this is like a teaser. my final point will be the following diagram. If x of t is White-Sand stationary, if I have a filter, LTI filter, with impulse response h of t, then let me call this y of t as my output. Okay. Then output process is also White-Sand stationary. Okay. This will be the point that we are trying to reach. Okay. So why is this important? Because in signal processing we have always some kind of filtering operation for noise removal, for enhancing some parts of the signal, etc. So this is a fundamental operation for us. For random processes, now I would like to extend my deterministic signal processing viewpoint to the random processes. So one way of defining these random processes is through White-Sand stationarity. And we see that if I apply an arbitrary, let's say, LTI filtering by h of t, I get another White-Sand stationary process at the output. But before that, I have to define something else. Before that, I would like to, it's just a definition. Jointly White-Sand stationary processes should be defined, will be defined. So what is this one? Jointly White-Sand stationary processes. So x of t and y of t are jointly. Now I have two processes, White-Sand stationary. Number one, x of t is White-Sand stationary. Number two, y of t is White-Sand stationary. And number three, this is something new. Rxy, t1, t2 is expected value of xt1, yt2 is a function of, again, as we have said before, time lags or lag variable, time differences. Okay? Again, I will try to call this as tau. So if x and y satisfy these three properties, they are called jointly White-Sand stationary. So the reason I need this is now I have input and the output process, x, y, and we will show that they are jointly White-Sand stationary. So y is White-Sand stationary, okay, this is what we are trying to show, but they are also jointly White-Sand stationary. This is just a definition. This is called, let me give, cross correlation. Again, function. Okay. So I just want to say that for complex valued quantities, in case, again, this second argument is conjugated. Okay. This is just a note. This is the definition. I have to conjugate one of them, but we are conjugating the second argument. So T2 is the argument after the comma, that is. Okay, that is the second argument. Now what else? Now let's go back to our main point. Okay. Let's say steps of showing y of t. Let me use small y. Y of t is White-Sand stationary. So let's remember. Now the problem is x of t, impulse response, LTI system with this impulse response, y of t. So this is White-Sand stationary. So the question is, okay, let me write a question. Let's determine the moment descriptions of output process y of t. That is it. So I need the mean and the autocorrelation function of this output process. I have to calculate them. Okay? That is the issue. So let me say this becomes the answer. Now, first of all, do we remember the convolution relation? Now, y of t is equal to minus infinity to infinity. H of, let me use dummy variable t prime, x of t minus t prime, dt prime. This is the convolution relation, am I right? H of t convolution with x of t. This is the relation between input and the output. Convolution relation in continuous time. It's something like this. We know lots of properties of this. They are commutative, associative, things like that, but this is good enough for our purposes. Now, question number 1 for Weissan stationarity. Let's find the mean function. So what is expected value of y of t? Okay. Expected value of y of t. Well, y of t is this. If I substitute it over here, so I need to find the expected value of this thing. Am I right? So every sample is processed by linearly combining some samples in the history, or maybe in the future, by these weights. That's the meaning of convolution. So I haven't done anything. Now, a critical step, since expectation is a linear operation, and this convolution operation is also linear, it's a bunch of summations, I can interchange expectation and integration over here. I can interchange that. We should be a little bit careful. The issue is this H it's not random. There is nothing random about H. This is your filter. Okay, this is a deterministic impulse response. There is not, these are just bunch of numbers. They are not changing. This H of t is not changing. So I'm adding things over here. And these are the weights of this. So I have done the following. This is the critical step. Exchange of expectation. And this, let's say summation, let's say. Sorry, we have this and dt prime. Am I correct? Now, how about this? What do I need? I need to evaluate this. But it says that this is Weissan stationary. Okay. So if this is Weissan stationary, then this is just constant, am I right? It's not changing by time. Constant. Since x of t is Weissan stationary. Am I right? So if it is just a constant, so let me write it over here, then this becomes minus infinity to infinity, it's just constant, dt prime. Okay, so this becomes, would you agree that this is something like this? H of 0, capital H of 0. So what is capital H? Maybe you can guess. Laplace transform of H of t. Okay. So this is just a number. That's my point. Okay. So this is the area. Take this out of integration. So this is the area under the impulse response, okay? The area from minus infinity to infinity, area under the impulse response, and this is just a number, whatever it is. Of course, if it is not infinity, I'll be very happy. If it is infinity, then this is an unstable filter, obviously, okay? This is an unstable filter, and I don't care about unstable filters because, this is a very practical problem, and our focus is the stable processing. I would like to do some operations on this signal. So you see, this is constant. Good news. So the first condition, condition number 1, output process has a constant mean. Okay, we have seen this. So the output process mean is nothing but input mean, and this is what we call in signal processing, this is called DC gain. Do you remember the frequency response topic? So this is the gain at the DC frequency, obviously. Maybe you can remember. So DC frequency is the zero frequency. Okay, that is it. In discrete time, it's the frequency of 1 in Z domain. But in the continuous time domain, now this is, as you see, DC gain when S is equal to 0 or omega is equal to 0. Well, things like that. S is equal to j omega. When omega is equal to 0, S becomes 0, etc. Things like this. Okay, so this is number one. Now we need actually more things. Let me use my other eraser. Now the autocorrelation function. Let's focus on the autocorrelation function. I think this wasn't hard, isn't it? This was rather easy. The second part is a little bit more difficult, but once you understand what is going on, it won't be, much different from the earlier one. Now the topic is whether the output autocorrelation is a function of T1 minus T2 or not. Okay. Now I would like to study this. This was for this. Now how can I handle this? So we will first, let's find our XY cross correlation T1, comma T2. You will see why. Okay, it will be easier to derive our RY from our XY. Okay, so our XY T1, comma T2 is. So this is expected value of X of T1, Y of, let me use the notation in my notes, a little bit simpler, T minus tau. So this is my T1, this is my T2, and time difference between them is tau. So this is by definition X of T, Y of T minus tau, and the conjugate. So I use this conjugate over here because, as I have said, it tells me that this is the second argument essentially. Okay, and of course that is the more general valid definition. Now what should I do? The same thing. Y of t is given over here. So this is expected value of. I will take the conjugate of y. Y of t is this. But I need yt minus tau. Some students make a mistake over here. So how do you find the t minus tau? So instead of this t variable, you should substitute t minus tau. Am I right? It's as simple as that. Instead of t, if you substitute 5, you get y5. So I need yt minus tau. I do the same substitution. T prime x of, so t minus tau minus t prime. T prime dt prime. Do you agree? Okay. Now I should take the conjugate, do the expectation. Now again, take the integral out. I have h conjugate, because of this, t prime, expected value of. As you see, not very much different from this one. Again, expected value goes in, but at the end I have a product. So this is the point where I use autocorrelation function. And I should have the conjugate over here, dt prime. So how about this part? Now this is the autocorrelation function, our x function, t comma t minus, because this expectation by definition, this. Am I right? By definition. But since this is White-Sand stationary, I will write this as an Rx function of time, evaluation time differences. This is first argument minus the second argument is. So this is my tau. So this is first argument minus the second argument. Okay. t minus t cancels, and minus these two minuses becomes plus. Okay. As we did before. So why am I writing it like a small rx function? Because it's a function of a single argument, as we have said many times. So this is this function of a single argument. Okay. Now this is then, at the end, if you give me this rx function, for example, in the earlier example, please remember this was sinc function. Sinc function, you know, with zeros at every integer point and so on. Okay? So this is the same function over here. Now here is the issue. Do you see a dependence on t on the right hand side? There is no t. So what has happened to the t's? After this expectation, I get, as I have said, t minus t operation, because time difference between those two samples is independent of this t value. Okay? So once this is Whitesan stationary, x is Whitesan stationary, due to Whitesan stationarity of this. So there is no t in the final, you know, cross correlation of input and the output. Okay? So let's make a note of this. No dependence on t. Okay. So this tells us that this can be written. Of course, if I do this integration, at the end, t prime variable will be vanishing. So this is a function of tau only. Okay? If tau changes, right-hand side changes, and that is the only thing. So no dependence on t variable, function of tau only. Function of tau, actually. This is a function of tau. But let me write this a little better. Do you think this looks like something that you know from, let's say, earlier discussions? Let me erase this. So this is almost like convolution, but it's not convolution, isn't it? So how can I make it look like a convolution? So this is the convolution relationship. I'm not erasing it for comparison purposes. Actually, I need something difference, isn't it? So I need this difference over here. So I don't have a difference, but these two are summed. So what can I do? So I will be writing it over here. Okay. So I will do t double prime is equal to minus t prime. If I do a change of integrals, sorry, change of variables over here, then what do I have? Minus infinity to infinity. Wow. Okay, let's do this carefully. Then h conjugate t prime is equal to minus t double prime. Rx, okay, tau minus t double prime. dt prime is minus of, there's a minus sign over here, okay? But if I do this substitution, this will be plus infinity, this will be minus infinity. There's a minus sign over here, let me also change their places. This becomes minus plus. Do you agree? So this is the change of variable that we do. Now, do you think this looks like a convolution? Well, if you don't believe me, just call this another function, g function, for example. Okay, so this is dummy variable t double prime. So this function, this differences, dummy variable is t double prime. So this is indeed a convolution. So this is convolution of this function and g function, am I right? This is the convolution of these two. So this becomes, it is actually its notation difficulties. So I have the following. This is equal to, let me write it like this, sorry. H conjugate minus tau convolution with Rx of tau. Do you agree? So, okay. So let me explain. This is my first argument of the convolution. This is my second argument of the convolution. So the first argument is actually this g function. So how do you get this g function? Actually, this is the flipped and conjugated version of the h function. Okay, that is it. So in the convolution relation, I use this g function. Instead of h, right here g, but g is equal to flipped version. then you do this. Dummy variable is integrated out. And at the end, the output variable becomes, at the end of this integration, classically it is t, convolution of two time functions, give you a time function. But here, output is tau. We have just said so it's a function of tau. This is a function of tau. So output is tau. So this impulse response with tau variable, conjugated and flipped, is convolved with Rx of tau. Okay? This is the notation. This can be a little confusing looking, but this is good news. Now I have a compact formula for this. So I see the following. This is equal to Rxy t, t minus tau. I have this. Now, our goal is actually not this one. This is good. But we want to show actually R YY. Am I right? But we will be using this. So let's go ahead. RYY or RY T1, T2. So again, I will do the following. Ry T, T minus tau. This is by definition expected value of, y of t, y of t minus tau, and I have conjugate over here. Let me see. Okay, so I have to calculate this. Now I'll be using this relation, yt. As it is. Nothing different. Y conjugate t minus tau, and that is it. I have this. So this is y of t, and I have yt minus tau. So again, let's move the expectation in. So I have to calculate expected value of this and that. So this becomes, if I write it like that, R x y t minus t prime, first one. Second one is conjugated. Okay. T minus tau dt prime. Okay. Expected value goes in. First argument is without conjugate, t minus tau. Second argument is with conjugated. Okay. So I have this. So this is equal to, actually, Rxy function, time differences of these two, because it does not depend on two arguments, but it depends on the difference of these two arguments. Rxy of tau minus t, t1 minus t2, t1, the first argument, minus t2, okay, gives you this. Minus t2 gives you plus tau, and I have this. So what do I have? Minus infinity to infinity, h of this, Rxy, tau minus this t prime, dt prime. Do you agree? So we have made use of this result over here. Rxy is a function of tau only. And I'm writing this, maybe I should write this before. I'm writing this as Rxy of tau. Okay? This is my Rxy of tau, a function of tau only. So how about this one? This one also looks like a convolution. Too many convolutions in a single lecture. And they're all looking like each other, but you know, they're a little different. So how about this one? How should I write this convolution? So this is, output variable is tau. If if I do this convolution, only tau will be read. So one of the arguments entering the convolution operation is h of t. So output variable is tau, then it becomes h of tau. Convolution with Rx y of tau, because t prime is a dummy variable. Now what do I have? Now the final thing is then Ry t minus tau s, let me write this, h of tau convolution with Rx y of tau. Okay? But this is equal to so I have, as you see, two convolutions in cascade for this calculation. So clearly, at the end of this is a one-dimensional signal in tau, another flipped version of it actually, but another one-dimensional signal in tau, another one-dimensional signal, and this is the autocorrelation function of this input process. Okay? So if you do such a convolution, so clearly this is a function of tau, and what we call, this would be called Ry of tau. This will be the output autocorrelation. Output autocorrelation. Okay. This is the end of White-Sands stationarity proof, as you see. Because if input is White-Sands stationary, we have seen that mean is constant. Just input mean multiplied by DC gain of this filter. Then output is also, in the autocorrelation sense, it's also stationary, because we see that it's only a function of the time differences. It's not a function of t over here, t's cancel. It's a function of tau only. So it's a big result. Furthermore, we have learned something new. They're also jointly White-Sands stationary. Input and the output, both of them are White-Sands stationary, but their cross product, this is this, which is called cross correlation of x and y. They're also a function of time difference tau. We have that. Okay, so we will continue from this point on in the next lecture.